Hello everyone, I welcome you all to the course of heat transfer. In today's session, we will discuss a couple of problems on radiation. Before we begin, let me give you some glimpse of the concepts that has been shared already with you related to the topic radiation. As you all know, radiation is the energy emitted by a matter in the form of electromagnetic waves as a result of changes in the electronic configuration of the atoms and molecules. And the governing law for the radiation of mode of heat transfer is being Stephen-Boltzmann law, which says the amount of radiant energy per unit area is directly proportional to fourth power of the absolute temperature. And if you take the equation, Q is equals to sigma into A into T to the power 4, where sigma is Stephen-Boltzmann constant, A is the surface area, and T is the temperature in absolute K. Now, we have also come across a term called total emissive power, which is the amount of energy radiated per unit area Then we have also discussed monochromatic emissive power, which is the amount of energy radiated per unit area, per unit time for a unit wavelength. Then we come across the term called emissivity, which is the ratio of emissive power of any body to the emissive power of a black body. Emissivity of a black body will be equals to 1, and generally emissivity of other surfaces will lie in the range of 0 to 1. Then we have also discussed the terms called as absorptivity, reflectivity, transmissivity to give you a little hint. If you consider a surface and allow some radiation onto the surface, then there will be 2 or 3 phenomena that will be occurring. One is absorption, and the one is reflection, and the one is transmission. Now, if you consider the ratio of absorbed radiation to the total incident radiation, this is called as absorptivity, denoted by symbol alpha. Next, if you consider the amount of energy that is reflected out of incident radiation, if you consider the ratio of these quantities, that is termed as reflectivity, denoted by the symbol rho. In a similar way, if you consider the amount of energy that is transmitted through the body to the total incident radiation, if you take the ratio of these, this is termed as transmissivity, denoted by a symbol tau. Now there could be all three phenomena occurring, or there could be two phenomena, or there could be one phenomena occurring. But all the time, absorptivity plus reflectivity plus transmissivity will be equals to 1. Now we have also seen a concept of black body where all the incident radiation will be absorbed and it will not reflect or transmit any radiation out of it. Hence, a black body is a one whose absorptivity will be equals to unity. In this case, the reflectivity and transmissivity is equals to 0. Next, we can consider an opaque body, in which case the transmissivity is equals to 0 and absorptivity plus reflectivity will be equals to 1. In simple words, an opaque body is a one which can create its own shade when light falls upon it. In a similar way, white body is a one whose reflectivity will be equals to 1. There will not be any transmissivity as well as absorptivity. Hence, for any white body, rho will be equals to 1 and alpha is equals to 0 and transmissivity tau will be equals to 0. We will come across one more type of body, which is a gray body. Generally, gray body is defined as a body in which the radiative properties, it could be absorptivity, reflectivity, or transmissivity, are assumed to be uniform over the entire wavelength of the spectrum. Such body is termed as gray body. Then we have also seen some of the laws. It could be Kirchhoff's law, which says emissivity is equal to absorptivity if a body is at thermal equilibrium with surroundings. Along with this, we have also seen a Wien Displacements Law, in which he conducted an experiment in order to relate the temperature with a wavelength precisely for a maximum emissive power, the corresponding wavelength and the temperature. It states the product of maximum wavelength and the temperature is constant, and that constant is around 2900 micrometer Kelvin. So you know the famous equation, lambda max into T is equals to 2900 micrometer Kelvin. Sometimes this equation can be used in order to know the temperature for a given wavelength. Then we have also seen a Lambert's cosine law, which states the total emissive power from a radiating plane surface in any direction is directly proportional to cosine of the angle of emission. To give you an illustration, so if you consider a candle flame, I can get a maximum heat energy at the top, and as you move towards the sideways, the heat energy goes on decreasing. Now, the same has been explained by Lambert. At the top, in the direction of flame propagation, the angle theta is 0. Hence, you will get a maximum energy because cos 0 is 1. And as you move sideways, theta goes on increasing, and if you reach an angle of 90 degree, cos 90 is 0. Hence, you will not get any energy. This was demonstrated by Lambert, and he has given the equation E theta is equals to En into cos of theta, where E theta is emissive power at any direction, Now we shall look into the problems that are related to the topic radiation. The first problem goes like this. Two large plates are maintained at a temperature of 900 Kelvin and 500 Kelvin respectively. Each plate has area of 6 meters square. There is a small correction here. It is 6 meters square. Compare the net heat exchange between the plates for the following cases. In the first case, you need to consider both the plates are black. In the second case, you need to consider the plates are having an emissivity of 0.5. Now, we have already discussed the emissivity, which is the ratio of emissive power of any body to emissive power of a black body. Now, when we consider both plates to be black, the emissivity becomes 1 because it will be emissive power of a black body to the emissive power of a black body, which is same in the numerator as well as denominator, which results into the value of 1. Now he has given the area to be 6 meters square. Please make this correction. It is 6 meters square, not 6 square. And he has given the temperature of the both surfaces is 900 and 500 Kelvin. Now, in order to find the net heat exchange between the plates, we need to take the help of Stephen-Boltzmann equation, which is as follows. Now, Q net from 1 to 2 is equals to sigma A into T1 to the power 4 minus T2 to the power 4 upon 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. So this term is called as equivalent emissivity. Now, if you consider the value of sigma, which is a Stephen-Boltzmann constant, to be 5.67 into 10 to the power minus 8, and area to be 6, and T1 he has given 900, T2 he has given as 500 Kelvin. The emissivity of both the surfaces is considered to be 1 because both are considered as a black body. In this case, there could be an alteration considering one body to be black and the body with the emissivity of some value. In that case, the body which is considered to be black, the emissivity value should be considered as 1. Now, if you substitute the values of emissivity epsilon 1 and epsilon 2, which are the emissivities of surface 1 and surface 2, as 1, and if you substitute the sigma value as 5.67 into 10 raised to minus 8, we'll have a value of 201.9 kilowatts. Now, in this problem, he has considered T1 by 100 to the power 4. With this also you will come up to the same solution. It is not necessary all the time to consider sigma value as 5.67 into 10 raised to minus 8. To substitute the value of T1 and T2 as it is 900 and 500 respectively. Now, in the second case, he asks us to calculate the heat transfer considering the surfaces with the emissivity of 0.5. Now, in addition to this, there could be one more question considering the emissivity of first surface to be 0.5 and second surface to be 0.3 or 0.2, whatever value. In that case, substitute the corresponding values in the equation. Now, in this case, if you substitute epsilon 1 and epsilon 2 as 0.5, so this becomes 67.3 kilowatts. The conclusion of this problem is that in case of black body, the amount of heat transfer is more compared to a gray body or any body whose emissivity is less than 1. So this again supports the statement black bodies are good absorbers along with good emitters as well as good emitters. If you see the value, it is almost 1/3 of the value compared to a black body. Moving to the next problem. The sun emits maximum radiation at lambda is equals to 0.52 micrometer. So this line has to be understood. It emits maximum radiation. Assuming the sun to be a black body, again this has to be considered. Calculate the surface temperature of the sun. Also calculate the monochromatic emissive power of the sun surface. Now he has given the maximum wavelength is 0.52 micrometer. You need to calculate the surface temperature. Now we have already discussed the surface temperature can be calculated using Wien's displacement law, which is the product of wavelength and the temperature is constant, and that constant is 2900 micrometer Kelvin or 2.9 into 10 raised to minus 3 meter Kelvin. This equation you can get from heat transfer data handbook at page number 82 in 6th edition. I'm referring to 8th edition. In 8th edition also you can avail this equation in page number 82. Now this is given, you are asked to calculate the temperature and you know the constant value. Now if you convert 0.52 micrometer to meter, is 0.52 into 10 raised to minus 6 meters. And if you calculate for the value of T, you'll end up with the value of 5576 Kelvin, which is the surface temperature of the sun. Now, if you need to calculate the monochromatic emissive power, which is given by the Planck's law, in heat transfer data handbook, you have this equation E suffix B into lambda is equals to C1 lambda to the power minus 5 divided by e to the power C2 upon lambda T minus 1. I have some constants. You know the value of lambda. He has given it to be 0.52 micrometer. It should be in meters. The constant values like C1 and C2, you can get the values again from the heat transfer data handbook. The value comes out to be for C1, it is 0.374 into 10 raised to minus 15 watt meter square. C2 is 14.4 into 10 raised to minus 3 into Kelvin. Lambda value you know, temperature just calculated as 5576 Kelvin. If you substitute the values, then you will have the monochromatic emissive power as 6.9 and 10 to the power 13 watt per meter square. Now this is the amount of energy emitted per unit wavelength. That is the definition of monochromatic emissive power. You can also calculate the total emissive power per unit area if you consider the expression would be sigma A into T to the power 4. If we consider the area to be 1, or if we calculate the total emissive power per unit area, sigma into T to the power 4. Again, he has made some mistake here. This should be 10 to the power minus 8, not minus 6. So if you substitute the value, you can calculate the total emissive power. As well as some cases, you may also ask to calculate maximum emissive power, which is given by the equation 1.285 into 10 raised to minus 5 into T to the power 5, where T should be in absolute scale. That is 5576 into 10 to the power 5. 5576 to the power 5. Now with this, I'll stop here. In next class, we will discuss some more problems related to radiation. Thank you.